Let's go ahead and get started again. Welcome back to the exciting conclusion of day one of this introduction to reinforcement learning. Let me quickly recap what we discussed before lunch and then we'll move on. So starting from the notion of the k-arm bandit problem, we baby-stepped our way towards a definition of the full reinforcement learning problem, which is based on the Markov decision process. The crucial additions being the notion of state, which can change over time, and the fact that the agent can affect the state and not just the reward through the actions that it takes. This gives rise to the credit assignment problem, and to address the credit assignment problem, we're going to need to engage in a long-term reasoning that was not necessary in the k-arm bandit problem, and which we have begun to formalize through the notion of return. So return being a discounted sum over the rewards that we can expect in the future, conditioned on the policy that we've chosen to follow. So then right before the break, we started talking about value functions. So value functions are just conditional expectations. So for every state that we can be in, the expected value of the return conditioned on that state and the policy that we have selected is called the value of that state. And similarly, the action value of a policy, the same idea, but now conditioned on the action, with the crucial point that the selected action may not be the action recommended by our policy. So it tells us the expected return given the current state and the current action, given that we commit to following the specified policy thereafter, but not necessarily in the current time step. Okay. So that brings us to the Bellman equation. So Bellman's great insight was that the definition of the value function can be rewritten recursively by making use of the transition function. So here, I'm going to, I think, stand over here so I can refer to the slides. So here we have a definition of the value function which is just directly in terms of this infinite summation. But we can rewrite that value function as a sum over the immediate reward that we will receive and the value of the subsequent state. But of course, we don't know what the subsequent state will be because it depends on, we don't know what the subsequent state will be, so we have to take an expectation over it. In addition, both the immediate reward and the state transition that yields that subsequent state themselves depend on the actions, and because we might have a stochastic policy, we're not sure what that action might be either, so we need to take an expectation across the action also. So here we have a notion that is used throughout reinforcement learning that is called bootstrapping. So the idea here is we take the immediate reward, but then rather than continuing to sum over rewards, we just bootstrap off of the value that we have already estimated for the subsequent state. And that already gives you a hint as to why the Bellman equation is useful, because we're going to reuse values that we computed for other states. Right, and again, so we're not sure what action we will take or what next state that will arrive in, so we take expectations with respect to them, yielding these two summations. Okay, so this is a recursive definition of the value function for a given state. We have one such recursive definition for every possible state in the state space. So what this gives us is a set of linear equations, and if we solve that set of linear equations, then we get the true value function for the given policy pi. And we can do something similar for the Q function. The only difference is that whereas here we bootstrap using the value of the next state, here we will bootstrap using the Q value of the next state action pair. And that means the order of these summations is switched, whereas here we didn't know what the action would be at the current time step because it depends on our stochastic policy. Here we do know the action at the current time step because it's an input to the Q function. However, now when we bootstrap, we have to bootstrap not off of a state, but off of a state action pair because we have a Q function, not a V function. And we're not sure how to supply that state action pair because we don't know what the next state will be. That's the stochastic transition that we take an expectation with respect to here. And we don't know what the next action will be because that will be selected stochastically by our policy at the next time step. So it's the same idea of recursively bootstrapping off of values in the future, just the only difference is whether we bootstrap off of a state or a state action pair. Okay, so the Sutton and Bartow textbook uses backup diagrams to illustrate how these Bellman equations work, and I think they're useful for intuition, so let's take a look at them quickly. So what I've written here, these equations are just repeating the Bellman equation from the previous slide for both V and Q. And what we have here in A is the Bellman equation for the value function. So the idea here is we start here at the root of this little tree, and we're reasoning about the value of the state corresponding to the root of this tree. Well, in order to compute the value of that state, we need to compute two expectations, and those expectations are shown here by a two-level expansion of this tree. So in the first expansion of the tree, we look at all the possible actions that our policy could select. So that corresponds to each summand in this first summation. Then, for each of those actions, once we select that action, it will interact with our stochastic environment and trigger a new state. And each of those possible new states corresponds to a leaf of this tree. So these are the two states that could result from selecting this action in this state. And for all the other actions we could have selected, there are similar stochastic outcomes. So this second inner summation, each of these summands corresponds to a leaf of this tree. Okay? So it's like a two-step look ahead, and then when we get to the leaves of these trees, we're going to query our value function to figure out what the value of the corresponding state is. And that will then provide the values needed in each of the summands here. Same idea for the Q value function, it's just that the states and the actions are reversed. So now we have an action at the root of the tree, because we've already specified the action as input to the Q function. We're going to look ahead at the possible states that could result from selecting that action. And then once we're in that state, our policy will then have to decide stochastically what action to take at the next state. So again, we have a two-level expansion just now with state action, with actions at the leaves instead of states. Okay. So everything that we've said so far about value functions and the Bellman equation was with respect to some arbitrary policy. So I give you some policy, it could be good policy, it could be bad policy, whatever. It has a value function, and if we want to define and reason about that value function, we can use the definitions in the Bellman equation that we just discussed. But of course, what we're really interested in doing is behaving optimally. So what we want to do is find an optimal policy, and in order to do that, we will need to reason about the value of the optimal policy. So this yields a notion called the optimal value function. So first of all, the key observation is that when we give every policy a value function, what we do is define a partial ordering over the policies. Right? So we can think of this in terms of all the possible states, okay? So we can say some policy dominates another policy, some policy pi dominates another policy pi prime, if for every state, it's the case that the value in that state is higher with pi than it would be with pi prime. Okay? But this is only a partial ordering because, of course, you can imagine a policy pi which is better in some states than pi prime, but worse than pi prime in some other states. So it gives us only a partial ordering. Those two policies would then be incomparable. However, in this partial ordering, it turns out that there's always, at the top, some optimal policy which dominates all other policies. So in fact, there can be multiple optimal policies. You can easily imagine, for example, a case where you're in a state and there are two different actions available to you, but those actions have the same value. So then you can define any probability distribution over those two actions and you'll get the same value. So you could always take one action, always take the other, mix them, flip a coin, whatever you like. So there can be many optimal policies, but all those policies will share the same optimal value function. Right? So this value function is achieved by taking a maximization over the policies of the value function. Right, and similarly for the action value function. Now the same idea of the Bellman equation can be extended to this notion of optimality. So just like we can use the Bellman equation to estimate the value of any arbitrary policy, we can use the Bellman optimality equation to reason about what the optimal value function for some given MDP is. Right, and so the idea is just to take the Bellman equation that we already had, and any place where we take an expectation over the actions, with respect to the given policy, we just replace that expectation with a maximization. So let's go back for a second. So this, remember, here was our value function, right? So we had an expectation with respect to the next state and an expectation with respect to action. So we're just going to take this first expectation and replace it with a maximization. Yes, yes. So this capital P here refers to the transition function, and the capital R refers to the reward function. Yes, so I can show you one sec. Hopefully my notation is consistent. Yes, the transition function is defined here and the reward function there. Yeah, so the probability of some S prime given an S and an A, and analogously for the reward function. Okay, so to define the Bellman optimality equation, we take that expectation over actions and we replace it with a maximization. Because we're not trying to reason about the value of some arbitrary policy, we're trying to reason about the value of optimal behavior. And if we behave optimally, then every time we have a choice, we'll take the choice which maximizes our value. Okay. And it's the same idea for the Bellman optimality equation for the Q function, for the action value function, but because the expectation that we had was over actions was inside, now the maximization is also inside. So this again can be illustrated using these backup diagrams, and in the Sutton and Bartow notation, maximization instead of expectation is just indicated with this line here. So this means over all these branches, we will take the max instead of the expectation. So this looks exactly like the backup diagram for the Bellman equation, just with this extra line. And similarly here, for the Q function, just the maximization happens inside. So that's a good question, but the question is premature. Because so far, all we're doing is defining these value functions. So we have a definition in terms of an infinite summation, and we have a recursive definition. In a little while, we will talk about algorithms for computing this, given a model, or learning it from data, at which point I hope your question will be answered. Okay? Yeah. So even though the value function defines a partial ordering, it's a partial ordering that ends in a point at the top. So there always exists at least one optimal policy. And there are never trade-offs in the sense that, oh, this policy is better here, but that policy is better there. If you have that situation, it's always possible to take those two policies and construct from them a single policy which has the best of both worlds. Yes, yes. Yes, so yes, there can be many policies with the same value function, and there can be many optimal policies with the same optimal value function. Yeah. Any other questions? Okay. Okay, so why are these optimal value functions useful? They're useful because if we are able to figure out what the optimal value function is for a given MDP, then we've actually solved the whole problem. Because all we need to do, given that optimal value function, is act greedily with respect to the value that we've computed. So this is easiest to see in the case in which we actually have our hands on the optimal action value function. So if we have this Q star, this optimal action value function, then we can extract an optimal policy from it by at every state simply performing an argmax over the actions that are available to us of that Q star, of that optimal action value function. So if we can find Q star, game over, the whole problem is solved. So that's why optimal value functions are useful. So notice, like, when we were reasoning about the Bellman equation, we started from some arbitrary policy as input, and then using that policy, we tried to reason about what is the value of that policy. With optimal value functions, we can actually go the other way around. We can reason about what the optimal value is for some MDP without ever explicitly writing down a policy. Once we have that optimal value function, then the policy becomes implied by it, because that policy is just greedy with respect to the value function that we've computed. Now, if we don't have this Q star, but we only have V star, then we can do the same trick, but it's a little bit more computationally expensive. Because we cannot directly access the optimal action, we have to do a one-step look ahead. So we have to say, okay, for every action available to us, we have to reason about, if I were to take this action, what reward would I get? What are all the possible transitions it could trigger? And then for those transitions, what's the value of each of the subsequent states? And then we have to compute an expectation with respect to that. So that's what this summation is for. So that we have to do a one-step look ahead, and the result of that one-step look ahead is the optimal action to take. So we can think of this Q value function as caching the result of that one-step look ahead. So if we want to avoid that computation later when we actually use the policy, then we'd be better off having Q instead of V. Okay, so this figure just shows a simple example. You have a simple task where you have to move around the world, and there's a couple points where you teleport. If you compute the optimal value function, then you get this table of numbers, and then from this table of numbers, you can just write down what the optimal policy is. And you can see there are some places where you have multiple choices because there are multiple optimal policies that all share this same value. Like, for example, in this square, I could go left or I could go up. It gives me the same value. Okay, so that brings us now to the algorithmic section to eventually get back to the question that was asked earlier. So what the Markov decision process does, it gives us a formal model of sequential decision-making. And what we mean by sequential decision-making is decision-making where we have to reason about a sequence of states. So that refers to the complication that exists in the MDP, but not in the contextual bandit problem. So, you know, as I said, if we can find the optimal value function, then finding an optimal policy is straightforward. So the whole game reduces to how can we find this optimal value function? And that's what the area of Markov decision planning is all about. Given a model, and by a model we mean given a perfect transition and reward function, how can we compute the optimal value function? And then using that optimal value function, we will act greedily in the world in order to obtain optimal behavior. Now, because planning methods, by definition, assume access to this model, we assume we know the transition and reward function, then we're normally not too concerned about this one-step look ahead that we have to do. It requires a bit more computation, but it's possible because we have, so here we will need to consult our model in order to do this one-step look ahead. This is the transition function here, which we will need to know in order to perform this one-step look ahead. So in the planning scenario, we had to assume access to that model anyway in order to do the planning. So it's typically no problem to do this one-step look ahead. And most MDP planning focuses on computing V star, the optimal value function. If we have the model now, but we won't have it later when we're deployed in the world, or if that one-step look ahead the computational cost of that is going to be an issue, then we can do MDP planning to compute Q star instead of V star. Okay. So Bellman's approach to MDP planning is called dynamic programming. And dynamic programming is kind of a funny name. So it does actually make intuitive sense if you understand what is meant by dynamic and what is meant by programming. So dynamic here, we can think of this as an old-fashioned way of referring to what we would now call sequential. So the problem is dynamic in the sense that the state changes over time. Unlike in a bandit problem where there is no state or there's only one state, the state of the world is changing over time. So this is dynamic. And programming refers here essentially to planning. So if you think about like, if you go to a wedding, then they might give you a program, which is like a schedule of events. So programming means coming up with that schedule of events, coming up with a plan, so it's planning. So it's like planning in a sequential world in which a state can change over time. Now, if you have a computer science background and you've studied, for example, the textbook of Corman, Lyserson, and Revest, or any other canonical computer science textbook, you may have encountered dynamic programming as an algorithm in a context that has nothing to do with planning or reinforcement learning. And that's because the idea behind dynamic programming has much more general application, and after Bellman came up with it, it was used in 100 other contexts and is now a sort of a generic solution strategy in computer science. And the main idea is basically you take a problem, you divide it into subproblems, you solve the subproblems, and then you reuse the solutions to those subproblems in order to solve the other subproblems more quickly. So this comes up in a lot of contexts. MDP planning is just one example and the sort of first example. So the idea behind dynamic programming in the context of MDP planning is as follows. We start out with some arbitrary policy, so this can be initialized however you like, and then we're going to perform policy evaluation. And policy evaluation means we're going to compute, using our model, the true value function for this arbitrary policy. So that's this step here that leads us to V. Now, given this value function, we're going to perform another step called policy improvement. And policy improvement means we're going to use the value function to figure out an incremental improvement to our policy. Now we've changed the policy, so our policy evaluation is out of date. We're going to repeat policy evaluation, find the value function of the new policy, repeat the improvement, and so on. And this process will repeat until we converge to the optimal policy and the optimal value function. Okay, so let's look first at how policy evaluation works. So the idea behind efficient policy evaluation is exploit the Bellman equation. So rather than estimating or computing the value of each state independently, we're going to use the Bellman equation to exploit the relationship between states so as to compute these values more efficiently. So here's the idea. We start with some initial value function. It's chosen arbitrarily. So in the context that we're looking at today, everything that we compute or learn is going to be tabular. So that means we just write it down in a big table. So our value function is, like a big vector, and for every state, it has an entry that says what the value of that state is. So we initialize that vector arbitrarily, that's V0. Now, we define an update rule for incrementally improving this estimate of the value function. And what this update rule does is it just takes the Bellman equation and turns it into an update rule. So this thing here is our update rule. It looks almost exactly like the Bellman equation. There are only a few differences. The first difference, instead of an equal sign here, we have a left arrow indicating this is an update operation. This is an algorithm, not a mathematical equation. And whereas on the left-hand side we have the true value of some arbitrary policy of pi, here we have the k plus first estimate of that value function. And this new estimate of the value function is computed by bootstrapping off of the estimate of the value function we had at the previous time step, right? So this is, we'd like to write down the value of this state, but we don't want to compute that infinite summation, so we're going to use the Bellman equation. So we're writing down the Bellman equation, and then we get to this part, and it asks for the value of the next state. But we don't know the value of the next state because we're trying to compute the value function. But we have an estimate of the value of the next state, which we computed in the previous time we performed this update, and so we just use that. So if we perform this update for every state in the state space, that's called a sweep. We sweep through all the states in the state space. We perform this update to go from VK to VK plus 1. Now, if we do a number of sweeps, then eventually this will converge to a fixed point, and that fixed point will be the true value of the arbitrary policy whose value we're trying to compute. So that's what's shown here algorithmically. I think I covered this already. So in the outer loop here, we have sweeps. Every time we repeat, we're doing another sweep. And in the inner loop, we're performing one sweep by visiting each state. And for each state, we're just going to perform this update based on the Bellman equation. And here, I think there's a termination condition when the update results in a change that's smaller than some threshold, we say good enough and terminate. Okay, so there were two steps to this process, policy evaluation and policy improvement. We just talked about policy evaluation. Let's talk about policy improvement. Okay, so when policy evaluation finishes, we have the true value of our arbitrary policy. So now what we want to do is use that to incrementally improve the policy. And we can incrementally improve the policy by trying to figure out if there's some state in which there exists some action that's different from the action recommended by our policy that we could switch to. So we're asking this question: is choosing some action A in state S and then using our existing policy better than just using our existing policy? That's the question we're going to ask. So in other words, is the Q value for this state action pair greater than just the value of that state, of the corresponding state? So now you can see why action value functions are useful, because they allow us to reason about these one-step variations in our policy. We have some policy and we say, what if just for this one state, just this once, we were to do something else besides what the policy says? Would that be better or worse? Okay? So if we can identify such a setting, then we can use that to improve our policy thanks to something called the policy improvement theorem, which says that if we change policy so that if we change our policy such that it takes this other action, doing so will increase its value. So intuitively, if it was better to take this action when we were in the state now, it would be better to take this action anytime we were ever in this state, which is equivalent to saying, let's change our policy to take that action in that state. All right, so for every state, if it's the case that, following this other policy yields a higher Q value, that's higher than the value of just following the original policy, then this implies that switching to that other policy will improve our value. That will yield a better policy. So in this case, we're doing this with just the only difference between the policies being the given state S, the action at the given state S. So if we do this for all states, then what the policy improvement step ends up doing is we take our policy and we change it to be greedy with respect to the new value function. So we had a policy, it was greedy with respect to its so we had a policy, we computed its value, now we change the policy to be greedy with respect to its value function, and then we go back and evaluate the new policy. Right, so we apply this principle at all states, and that gives us a greedy policy. We change our policy to be one that is greedy with respect to the value function that we just computed. Now, if we ever do that, if we ever try to do policy improvement, and we find that the result of policy improvement is the policy we already had, so we started with some policy pi, we did policy evaluation to figure out q pi, and then we tried to do policy improvement, but the result of policy improvement was pi prime, and we found out that pi prime was the same as pi. This would imply that, we had the optimal policy. Because if the policy before and after are the same, then that means the value function of the two policies is the same, which means the value function of the new policy is equal to this quantity here. So if we look up here, when I do policy improvement, I'm taking an argmax with respect to this quantity, right? So I take the argmax with respect to q, but if I don't have q, I have to do the one-step look-ahead. This is what the one-step look-ahead looks like. Now, so this is going to be my new policy. It's going to be the result of this argmax. What is the value of that new policy? It's just the max that corresponds to that argmax. So that's what's here, right? So what is this thing? This quantity, which is implied by the fact that the policy didn't change, this is itself the Bellman optimality equation. So if I try to perform policy improvement and I get back the same policy I started with, that implies that that policy satisfies the Bellman optimality equation. And if it satisfies the Bellman optimality equation, it's an optimal policy. So that means we're done planning. So this is how this process works. We alternate between policy evaluation and policy improvement. Every time we do policy improvement, our policy evaluation becomes obsolete. So we go back and repeat policy evaluation, and then we have we have the opportunity to do more improvement based on the new value function. So this is my favorite figure from the entire Sutton and Bartow book because it captures this process quite well. So here's the idea. We start out with some arbitrary v and some arbitrary pi. So pi is just some policy. It might not be good. And v is not even necessarily the value of any policy. It's just some random numbers we wrote down in the table representing our value function. Okay? Now the first thing we do is perform policy evaluation. And what policy evaluation does is it drives us towards this line. And what is this line? This line is all the places in which v, which is the value function represented in our table, equals the true value of our current policy. So if these two data structures representing our value and our policy, if they are consistent in the sense that v equals v pi, then that means we're on this line somewhere. Okay? So we've completed policy evaluation. Now we do policy improvement. Policy improvement drives us to this line. And this line corresponds to all the points at which our current policy is greedy with respect to the value function. And policy improvement makes that true. Okay, but when we've completed policy improvement, the value function is no longer the value function of our policy because we changed the policy. So now we have to go back and do policy evaluation again. This process iterates, but converges inexorably on this fixed point where both of these conditions hold at the same time. Yeah? Yeah. Why is that? Can we give some intuition about that? So it's a consequence of the policy improvement theorem. Did the mic go out? There we go. The best way to get intuition about it is to think about if it wasn't true, then that would mean that there would exist these trade-offs that I mentioned earlier. Like there'd be a policy that would be good here and a policy that would be good there. But if that's true, it's always possible to combine those into a policy which takes the actions it should of policy 1 here and the actions of policy 2 there and gets the best of both worlds. So let me try to put that another way. So what we're doing when we do MDP planning is we're finding the best closed loop policy. And a closed loop policy is a policy that conditions on the current state. Okay? So this is in contrast to open loop planning, where an open loop plan is like just a sequence of actions you prescribe in advance. Like you go to Google Maps, it asks you how to get there. It just gives you a list of steps. Those steps don't condition on any information you'll get along the way. So what we're doing here is closed loop planning, not open loop planning. And because we're doing closed loop planning, we always have the opportunity to condition on the current situation. So we're never committed to some bad path. So if we have a policy which is good in some regions of the state space, we can follow that policy in that region only and do something else elsewhere. So I have a slide coming up which I think might give some more intuition about this later if that's still fuzzy. There was another question over here? So the naive approach is every time you do policy evaluation, you perform a series of sweeps across the state space. In each sweep, you visit every state. And you do many sweeps until the changes to the value function are below some threshold you consider acceptable. You're computing the true value function of the current policy. Yeah? Was there another question over here? Yeah, so the proof is beyond the scope of this course, but it's possible to show that the Bellman operator is a contraction mapping. So that means regardless of how you initialize the policy and the value function, you will inexorably get closer to that fixed point. Yeah. Yeah. Other questions? Okay. Okay. So this slide gets to the question that was earlier. So what's on this slide is a counterexample, which is false, okay? So this counterexample purports to show why dynamic programming would not converge to the optimal policy. So this gets back to the question that was asked a minute ago. So the counterexample obviously is wrong because it is guaranteed to converge to the optimal policy, but we need to think about why. So here's the counterexample. Suppose we have an environment in which the agent has two actions. It can go left or right. And we have a finite horizon scenario that lasts 2 time steps. So the agent has 2 choices to go either left or right. And let's suppose we get the following return for the different policies available. So let's suppose the agent goes left twice, then it gets 5. If it goes left and then right, or right and then left, it gets 0. And if it goes right twice, then it gets 10. So according to this counterexample, if we start from left-left, we would appear to be in a local minimum. Right? This is probably the intuition that you have as to why this might not work. So, you know, if I'm at left-left and I switch to either left-right or right-left, it only gets worse. So I go back to left-left and I stick with 5, but I never get to 10. So does anyone have a thought as to what's wrong with this counterexample? Yeah? What do you mean by that? Yeah, so I haven't actually said what the state is, but I think you're on the right track. So I didn't say anything about how the state was defined. How do you know it's not Markov? Okay. Okay, so we have a scenario in which the agent has the opportunity to take 2 actions, so the horizon is of length 2. So the game will last 2 time steps. And if the agent takes left twice, it gets 5. If it takes right twice, it gets 10. Anything else yields 0. So it would appear that if we start from left-left, from that policy, we would be in a local maximum. If we try to change our policy to left-right or right-left, we will get worse. So that we would appear to be stuck and unable to reach right-right, the optimal policy. So your comment, I think, is the right intuition, but I didn't actually say anything about how the state was defined, right? So it's not clear from this that it's not Markov, right? Like I could define the state such that, you know, the reward is 0, unless you're at, you know, one of these 2 terminal states, in which case you get 5 or 10. But the state is an important part of the argument. Does anyone else have an idea? Yeah?
This counterexample only takes into account the return of a action, but it doesn't take into account the value of state. While our own equation actually do it.
Yeah. Yeah, so as I hinted at a moment ago, when we do dynamic programming, we're finding closed loop policies. And what we have here are open loop policies. So in a closed loop policy, we have the opportunity to specify what action we take for every possible state. So that includes states that may never be visited by the current policy. Right? So if I have a policy that says that results in me taking left twice, there still exists in that policy somewhere an action specified for whatever state I would be in if at first I had done right. And if at first I had done right, whatever state I would end up there, I will have a choice between doing left and right at the next time step. And I will see through my dynamic programming that going right is better than going left. And then as that value propagates back up to the top, I'll realize, hey, I should go right from the beginning because that will lead me to a state where I can go right again, which will give me a payoff of 10. So remember, we're doing closed loop planning. The policy is specified for every state, even states not visited by the current policy. And that allows, you know, if anywhere there's good reward to be had, that will be discovered by the planning process, and that information will propagate back through to any state from which that reward is reachable. So if it's worth going to that state, that path will be discovered by dynamic programming. Okay? Okay, so what we've talked about so far is an algorithm called policy iteration. And policy iteration does what we just described. It iterates between policy evaluation and policy improvement. This is always guaranteed to converge, but it might be slow. And one reason that it might be slow is that it does an entire run of policy evaluation before it moves on to policy improvement. And remember, policy evaluation in itself requires not just one, but many sweeps of the state space. So a natural question is, can we speed up this process by terminating policy evaluation earlier? And the answer is yes. Actually, any amount of policy evaluation will be fine and won't affect the convergence guarantee. So we can terminate policy evaluation whenever we like in the middle. We can say, hey, we're going to do 5 sweeps instead of 100, or we're only going to do 1 sweep, or we're not even going to do an entire sweep. We're just going to select a few states and update them, and then move on to policy improvement. And there's a trade-off here in the sense that the more time we spend on policy evaluation, the higher the quality of the improvement we will do when we do policy improvement. So we can either do many policy improvements that might not be very good because they were based on sketchy policy evaluation, or we can do fewer policy improvement steps, but they'll be really high quality because they'll be based on a laborious policy evaluation we did. In the most extreme case, if we go all the way from policy iteration to the other extreme, where we say we're only going to do policy evaluation on a single state before immediately switching back to policy improvement, we get an algorithm called value iteration. And the policy evaluation is so short in that case that it can be integrated into the policy improvement in a single update rule. Okay? So this is what the update rule looks like. So we have a single, we had VK, and we're going to write down VK plus 1 by just sweeping through the state space and applying this update rule. And in this update rule, this summation here can be thought of as like a mini policy evaluation just for the current state. And then, before we even write down the result of that, that little bit of policy evaluation, we're going to immediately maximize with respect to it, immediately perform the greedification policy improvement step, and write down the result of that in our new VK. So policy evaluation and improvement are packed together in a single update. And the nice thing about this is it, just like the policy evaluation update rule took the Bellman equation and turned it into an update rule, here we've taken the Bellman optimality equation and turned it into an update rule. So again, this looks exactly like the Bellman optimality equation. We just have an update sign instead of an equals, and we have here estimates of the value function instead of the true value function. So we start with some arbitrary value function. We keep applying this update rule until it satisfies the Bellman optimality equation, and then we stop. Okay, so that's a whirlwind tour of dynamic programming, which is the core method for planning and Markov decision processes. So this means given a model of the world, we solve the computational problem of finding the optimal value function and therefore the optimal policy. Okay, so what we're going to do now is baby step our way to reinforcement learning by removing the assumption that we have a model and instead taking a data-driven approach to estimating these value functions. So the first baby step there is something called Monte-Carlo methods. So you're probably familiar with Monte-Carlo methods in general. They're statistical techniques where you use a bunch of samples in order to estimate quantities. So we're just going to apply that idea here to say, anytime we need to consult the model, but we no longer have a model, we'll just draw samples from the world. And then we'll use those samples to estimate the same quantities we would have computed if we'd had a model. Okay. So Monte-Carlo policy evaluation in its simplest form does exactly what I just described. We have some arbitrary policy, we want to know its value function, but we don't have a model of the world. But we can interact with the world. So what do? We use the policy by interacting with the world for a number of episodes. And then for each state, we just compute a sample average of the returns that we observed after visiting that state. And there are two variants of this, one where we average over all the visits to the state that we saw in an episode, and one where we average only the first visit of that state in an episode. They both converge. There are some empirical pros and cons that aren't very important. So this is what the backup diagram looks like for Monte-Carlo methods. Whereas in dynamic programming, the backup diagram was a tree. That tree expansion is no longer possible because that tree expansion relies on querying the model for a bunch of counterfactual scenarios. What if I ended up in this state? What if I took that action? We don't have the model, so we can't perform those counterfactuals. We can't construct the tree. But what we can do is interact with the world and generate a bunch of sample rollouts. And those sample rollouts are not trees, they're chains. So this is what the backup diagram looks like for a Monte-Carlo method. We're trying to estimate the value of this state. We perform a rollout. When we get to a terminal state, we add up all the rewards we got along the way. That's a sample return, which we feed into our sample average. Right. So unlike dynamic programming, the computational cost of this is going to be independent of the size of the state space because it's just, we just perform rollouts in the world, regardless of how many states there are in the world. Right, so in the planning setting, when we had a model of the world, we said we could compute V or we could compute Q, but we'll probably normally be happy with V, because V will require us to do a one-step look ahead when we use the policy later, but that's okay because we needed the model to do the planning anyway, so we'll just use that same model to do the one-step look ahead. But now we've removed the assumption that we have a model, so we're learning through interaction with the world, and that means just computing V star by itself is not going to be that useful. Because even if we have V star, we won't know how to act in the world because it will require a one-step look ahead that we can no longer compute without our model. So that means we're going to be a lot more interested in estimating Q star, and we can do that with the same Monte-Carlo approach, but the exploration problem that we saw in the K-arm bandit problem is going to rear its head again. So in order to learn Q star, we're going to need to learn good estimates of the expected return for every possible state action pair. Not just the state action pairs visited by the policy that we're using to interact with the world. That means we're going to have to take whatever policy we're using to interact with the world and add exploration to it in order to ensure that we get data about enough state action pairs to have a good estimate of the value function. So this Monte-Carlo estimation will converge if every state action pair is visited infinitely often. So in other words, if we do sufficient exploration. So then if we want to do control, if we want to find an optimal policy, not just evaluate an existing policy, the paradigm is the same as before, only we've replaced policy evaluation with Monte-Carlo evaluation. So whereas before we would do policy evaluation using dynamic programming in our model, here instead, we're going to do the evaluation by just trying out the policy a bunch of times in the world to estimate its Q value. And the policy improvement step will look the same. We'll just greedify the policy with respect to the value function that we estimated using Monte-Carlo samples. Okay, so now in the control setting, there are two kinds of Monte-Carlo control that we can do. On policy and off policy. And the difference between on policy and off policy is kind of a crucial foundational concept in reinforcement learning that will come up again and again. So let's talk first about on policy Monte-Carlo control. So on policy here means that the policy whose value function we're estimating is the same as the policy that we use to interact with the world and gather data. So if this policy explores, then we are learning the value of that exploratory policy. Right, so we have some, let's suppose we take the most naive approach to exploration, epsilon greedy. So we have some epsilon greedy soft policy. So when we do on policy Monte Carlo, we learn about the value of that exploratory policy. And then when we do greedification, we don't want to take an argmax because that argmax would get rid of all the exploration. If we did the argmax, we'd end up with a deterministic policy, so when we went back to policy evaluation, there'd be no more exploration. So instead we do a soft greedification, which retains this, this epsilon greedy exploration, and thanks to the policy improvement theorem, we know that, that this epsilon soft policy will still be an improvement. So in this way we can learn about the policy that we're gathering data about, and we can ensure good estimates of our Q function because we're exploring sufficiently, with the caveat that when we converge, we won't converge to the optimal value function or the optimal policy, we'll converge to the best epsilon soft policy. So given the constraint that we have to do epsilon exploration, we'll find the best policy that satisfies that constraint. Now, of course, we can reduce the amount of exploration over time. We can anneal it according to a schedule, though deciding on that schedule may in practice be tricky. So that's a little bit unsatisfying. We can get around that by going off policy instead. And off policy means the policy whose value function we're estimating is different from the policy that we use to gather the data. And that may seem too good to be true. How is that even possible? But it is possible. And it's a key concept which is used throughout reinforcement learning. So this is useful, for example, if you aren't able to control the behavior policy, like you're trying to optimize some search engine and you have to do it using data that was gathered by the existing search algorithm. And you work for Google and Larry Page won't let you just monkey around with his search algorithm. So you have to learn from whatever data is coming in from the existing algorithm. Or in many cases, what we're actually interested in learning about is a deterministic policy, because deterministic policies, they have lower variance, and we know that there always exists an optimal deterministic policy. But in order to explore, we typically want a stochastic policy. So we'd like to learn about a deterministic policy using data gathered by a stochastic policy. That will require us to be off policy. So we can do that using importance sampling. So this slide is a one-slide refresher on importance sampling. I think this is a concept that's probably familiar to most of you, but if it isn't, or if you need a refresher, here it is. So in importance sampling, we're interested in estimating the expected value of some function with respect to some random variable d. So d is called the target distribution. It's the distribution of interest. But we want to do so using samples that were gathered from another distribution, the source distribution, d prime. This is sometimes also called the proposal distribution. Okay? So the two distributions are known to us, but this function f is not known. So that's why we want to estimate its expected value from samples. Okay, so importance sampling is based on the following observation. In fact, this is a proof of the correctness of the importance sampling estimator. So this is the thing we want to estimate, the expected value of f under the distribution d. Okay? So this right here, this summation, this is just the definition of the expectation. Now I can rewrite that expectation as this quantity. I've just taken that summation and I've just multiplied and divided by this new quantity d prime of x. Okay? Now this quantity can itself be interpreted as a different expectation with respect to d prime. So whereas here this was the probabilistic weighting of my expectation, now I just use this as a probabilistic expectation of my weighting. So now I get a new expectation of this weighted quantity, and that expectation is equal to the expectation of the original of f with respect to the original distribution, so the quantity of interest. Now, instead of computing this expectation directly, I can estimate this expectation from data using the importance sampling estimator. So I just draw a bunch of samples from the source distribution, weight them according to these importance weights, this importance ratio, and then when I put them together, I have an unbiased estimate of the quantity of interest, the expected value under the target distribution. So in our case, the target distribution will be the estimation policy, the policy whose value function we're trying to estimate, and the source distribution will be the behavior policy, the policy that we actually use when we interact with the world. Okay, so if we apply this to our Monte-Carlo control setting, we have a bunch of data that was gathered, from some policy pi, and we'd like to, that was gathered from some policy pi prime, and we'd like to use it to estimate the value of some policy pi. So this is just an application of the importance sampling estimator, which is defined here. Now let's look at these importance ratios. The numerator and the denominator in this importance ratio, these are the probability of the return that we observed being generated under the source policy or the target policy, under the behavior policy or the estimation policy. So what is the probability? What's the probability of some particular return that you observed happening? Well, it's just the product of all the probabilities that built up that return. So it's the product of all the transition probabilities that occurred, to result in the sequence of states that were visited along the way, times all the policy probabilities. So all the actions that you took along the way, those were all selected from some stochastic policy according to some probability. So this numerator and this denominator that make up these importance weights is just a product of all these probabilities. Now the nice thing here is that, in this ratio, we have some terms here that we don't know, right? These here are transition probabilities. We don't know the transition probabilities because they depend on a model that we no longer have. That's why we're doing Monte-Carlo in the first place. But they're exactly the same in the numerator and the denominator, so they happily cancel, and the importance ratio can be computed even though we don't have a model. The importance ratio ends up being a ratio only of the policy probabilities. So in this way, we can do off-policy Monte-Carlo control, learn about one policy from data gathered by another policy. Of course, if you've ever worked with importance sampling, you know it's not a silver bullet. While it gives you an unbiased estimator, that estimator may have arbitrarily high variance, and these importance weights can be really large or really small, and basically controlling the variance is going to depend a lot on the similarity between the two policies. So if the policies differ too much, our ability to estimate the value of the target policy may be extremely limited. Any questions before I move on to temporal difference methods? Yeah. So that's a good question. So these simple Monte-Carlo methods that I've talked about so far, they converge only in the limit. So we can't say anything about bounding regret. Later, we're going to talk about starting now, we're going to talk about temporal difference methods in Q-learning and the sort of canonical reinforcement learning methods. They are more efficient in practice, but they also converge only in the limit, unless you do some very careful and clever things with exploration. There are reinforcement learning algorithms that have stronger guarantees. I have a slide about this, but I think it's not till day 3. So there are reinforcement learning methods with pack guarantees, where you can talk about the sample complexity, the number of samples needed before we can say that with high probability we have an approximately correct policy. Or there are also regret bounding reinforcement learning methods that extend regret bounds from KRM bandit problems to the full MDP setting. They do require some restrictive assumptions, and they perform very poorly in practice. So even both these pack MDP and regret bounding methods, they work on only extremely small MDPs, but they have the best theoretical guarantees. I'll talk a little bit more about that later. Yeah. Yeah. So dynamic programming assumes a perfect model. It doesn't reason at all about imperfections in the model. So if we don't run out of time on day 3, we will talk a little bit about model-based reinforcement learning, where we don't assume we're given a model, but we take our data and we use it to learn a model. And then we're going to plan on the learned model. And there, the more sophisticated methods will actually reason about model uncertainty. So you can, for example, from a Bayesian perspective, maintain a posterior about what the unknown model is. And then when you plan with respect to the model you learned, you take into account that uncertainty. But again, that's quite difficult to do in a scalable way. That's the kind of thing that can be done on toy problems, but not on hard problems. Okay, so the final topic that I hope to cover before we run out of time today are temporal difference methods. So temporal difference methods are the foundational methods of reinforcement learning, and we've kind of been coming at it from 2 different angles. So on the one hand, we started from dynamic programming, where everything is based on the Bellman equation. But we had this restrictive assumption that we had to have this magical model that would tell us all these transition probabilities and rewards. On the other hand, the other approach was Monte-Carlo methods, where we didn't even mention the Bellman equation. I don't know if you noticed, but we didn't even mention the Bellman equation. Everything was just based on sample returns. But we didn't need a model. So temporal difference methods bring these 2 threads together to methods that get the best of both worlds. We're going to do bootstrapping that is akin to the Bellman equation. So we're going to exploit the great insight behind the Bellman equation, but now in a sample-based way. while retaining the property that we don't need a model, that we can learn purely from data. Okay. So the first temporal difference method, the simplest temporal difference method, is called TD0. So TD stands for temporal differences, which is what the update rule is based on. And it's a method which estimates V pi. So we're trying to do policy evaluation. We have some arbitrary policy. We're trying to estimate its value, but without a model, but using data, but we want to exploit something that looks like the Bellman equation. Okay, so the easiest way to understand, and the 0 refers to something called eligibility traces, which we'll talk about a little bit later. So you can ignore the 0 for now. The easiest way to understand temporal difference methods is to first define a slightly different Monte-Carlo method and then compare them. So in the Monte-Carlo methods we talked about, we said, okay, we're going to collect a bunch of sample returns and then we'll compute a sample average from them. So we can do something slightly different where we maintain a running estimate of the sample average, and then every time we get a new return, we update that sample average. Okay, so that's what's shown here. So instead of collecting a bunch of returns and summing them up, we always have a running estimate, and then we just fold the new return into that estimate using this update rule. And this learning rate is going to determine, how much weight we put on the new return compared to the old returns. So this will result in an exponential averaging of the different returns that we collected. Okay? So now, if we think of this part of the update rule as an error term, because it compares the return that we just observed to our estimate of the expected return, if we think of this an error term, then we can create different update rules where we just change what the target of that error term is. So this is the thing that we're trying to estimate, and this update rule is going to move it closer to this target that we just got from the data. All right? So what we do in TD0 is we just use a different update target. Instead of using a sample return, we're just going to use a single sample reward, and then on the next state, we're going to bootstrap off of the value of that state that we arrived at. Okay? So we can think of this thing here. This is a new temporal difference update target that replaces a sample return. We can think of this as like a sample-based estimate of the Bellman equation. So whereas the Bellman equation asked us to consult the reward function for the expected immediate reward, here we'll just take a sample immediate reward and use it as a proxy. And whereas the Bellman equation required us to perform an expectation over the next states, where that expectation is with respect to transitions governed by the transition model, here we'll just use a sample transition. Look, we were in this state, we got some reward, and we had a sample transition occurred that resulted in ST plus 1. We'll just bootstrap off of that sample transition. So this is like a data-driven estimate to replace the Bellman equation that we're no longer able to compute. So this is called a bootstrapping method because here we're bootstrapping off of the value of the next state, just like the Bellman equation does, even though we don't have a model. So yeah, this is the pseudocode. I think the idea here is intuitive. So every episode that we interact with in the world. Okay, was there a question? I don't know where that came from. So we select an action according to our policy. We take that action, we observe some reward in some next state, we use it to perform a temporal difference update, bootstrapping, and then the process repeats. So this is what the backup diagram looks like. If you hadn't noticed, the backup diagrams are getting simpler and simpler. So the temporal difference backup diagram was like wide but shallow. It was wide because we had this model so we could compute all these expectations. These expectations require expanding all these branches of the tree that result in it being wide. But because we bootstrap, the tree was shallow. We only looked ahead 2 steps, like one action and one next state, and then we bootstrapped off of the values at the leaves. So the tree was really shallow. Whereas with Monte-Carlo methods, we had something that was very narrow but deep. We didn't have the model, so we couldn't do all that branching, but we weren't using the Bellman equation, so we had to wait till the end of the episode to actually see how the return turned out. Whereas here, we're getting the best of both worlds, so there's no branching because we don't have a model, we just have one sample, and when we get to the next state, we just bootstrap off that next state without waiting to see how the actual return plays out. So that results in this very simple backup diagram. Okay, so, like Monte-Carlo methods, TD methods require only experience. We don't need a model. Unlike Monte-Carlo methods, they can be fully incremental. So that means that every time step we perform some update, we don't have to wait until the end of the episode to do some learning. Which means we have less memory requirements. We don't have to save this return along the way. We can just do the update and then move on. And we don't have peak computation where at the end of the episode we suddenly have to do a lot of computational work. The computational work is distributed throughout time because at every time step we get another sample and we can immediately do an update based on that sample. We can also, we don't have to have entire sequences like we would with Monte-Carlo methods. If I just give you a pile of samples that are in no particular order and aren't connected into episodes, you can still learn from them. Right, they both converge, but temporal difference methods tend to converge faster, and the intuition is the same as it is behind dynamic programming. We're using the Bellman equation to bootstrap, to reuse the solution to other subproblems. We already have an estimate of the value of the next state, so we can bootstrap off of it without having to estimate it anew from a fresh sample return. So it tends to converge faster. Okay, so TD0 is a temporal difference-based policy evaluation method for estimating V-pi. We can also estimate Q-pi using SARSA, which is a related algorithm. So SARSA is actually an acronym, well, it's not an acronym, but it's called that because it refers to the elements that appear in the update rule. The state, the action, the reward, the next state, and the next action, SARSA. So here's what the update rule looks like. And it's exactly what you would expect based on TD0. So again, this is our estimate of the Q function, and we're computing an error term that compares it to some target. And this target is constructed in this Bellman equation-like way based on a sample return, but now bootstrapping off of the value of the next state. Bootstrapping off of the value of the next state-action pair. That's what I meant to say. Other than that, the idea is exactly the same as TD0. Now, the SARSA algorithm is kind of a source of confusion because the way I've presented it to you now, which I think is the right way to think about SARSA, is as a policy evaluation algorithm. It's exactly analogous to TD0. It just estimates Q-pi instead of V-pi, okay? But normally, we think of SARSA not as a policy evaluation algorithm, but as a control algorithm. That is, an algorithm for estimating Q star, not Q-pi. An algorithm for finding the optimal policy by finding Q star and then behaving greedily with respect to it. And we can understand why by looking at this pseudocode, which shows you a kind of typical application of SARSA. So what would typically happen is you have some soft, greedy policy. So you have some value function. When you act in the world, you're going to act soft, greedily with respect to that value function. So basically, you're going to be greedy with respect to that value function, but you'll throw in some exploration, some epsilon greedy exploration in order to ensure sufficient coverage of the state action space. Then, when you do this SARSA update, we can still think of this SARSA update as doing policy evaluation, but it's doing policy evaluation of this soft greedy policy. So every time we do policy evaluation, we change the greedy policy, the soft greedy policy that we will use to gather the further data. So we're doing policy evaluation, but we're doing policy evaluation of a moving target. So whereas, in dynamic programming, we said we do policy evaluation, then once we've finished policy evaluation, we do policy improvement, and then in value iteration, the two were kind of intermingled. Here, they're intermingled in a new way. The policy evaluation happens here in the update rule, right? Whatever policy generated this data, we're going to estimate that policy by applying this update rule. But as soon as we change that estimated value function, we will change the policy that's used to gather the new data, and therefore the value function that we're trying to estimate. So we can think of the policy evaluation happening here in this update, and the policy improvement happening out in the world. Policy improvement happens out in the world when we act soft greedily with respect to whatever value we've estimated. And then because we're doing policy evaluation based on the data that we gathered from the world, this is now on policy, we will then be evaluating this new updated policy. So the policy evaluation is always tracking the policy that we're using to act in the world, which is itself always tracking the value that we're estimating by being soft greedy with respect to it. So there's an interesting variant of SARSA called expected SARSA. And the observation behind expected SARSA is that in the SARSA update rule here, we have where everything is learned from samples, right? So there's going to be a lot of variance in these updates. And some of this variance comes from the sample transition, because we don't know what the next state is, right? We don't know what S prime is, so we just take the sample S prime that occurred when we actually acted in the world. But SARSA also uses a sample A prime, and this sample was generated from a policy, our own policy, the policy we use to act in the world. And the distribution governing that policy is known to us. So we don't have to use a sample action here, we can compute that expectation explicitly. And that's what expected SARSA does. So we just replace the sampling over actions with a summation over all the actions, and for each action we query our known policy for the corresponding probability. So then the sample here is only with respect to the next state. We still don't know the transition probabilities, so we have to rely on a sample transition, but we do know the policy probabilities, so we can compute an expectation with respect to them. So this, if you can do the computation to perform this expectation, which in many cases is negligible, then you can reduce the variance of your SARSA updates. Okay. So from Monte-Carlo, we went to TD0 by reintroducing this Bellman equation-like idea. Then from TD0, we went to SARSA, same idea, but just for Q functions instead of V. And if we do these policy updates in the world, then we get a control algorithm. We can actually approximate Q star. The final step towards Q learning, which is the canonical reinforcement learning algorithm, is to go off policy again. So remember, in the Monte-Carlo setting, we said we can do this on policy, or we can do it off policy by gathering data with one policy and using it to learn about another policy. So we can do that in the temporal difference setting too, and that's exactly what Q learning does. So whereas in the SARSA algorithm, we take a sample action, the update is based on a sample action, and in expected SARSA, we take an expectation across actions. In Q learning, we take a maximization over those actions, right? So this is now our new target. It's based on a sample return plus a maximization over the actions with respect to the Q value of the subsequent state action pairs, right? So does anyone have a clue why this is off policy? Yeah, so when we perform this maximization here, the result may be an action that is different from the one recommended by our current policy. So when we were gathering data in the world, we were doing it with respect to our current policy. But when we do policy evaluation, we say, forget about that policy. Who cares what action that policy actually took in the next state? Let's just consider the value of the best action by performing this maximization. So we're learning off policy. So now, the tricky question, what happened to our importance sampling estimates? What happened to the importance weights? There aren't any. Why not? Does anyone have a clue? It's unclear exactly what you mean by that. So we're off policy for the reason we just discussed. So we're learning about a given policy, but we're gathering data with a given policy, but we're doing policy evaluation about a potentially different policy that takes the max action. So there is a difference there. Sorry? Why? Why is it one? Yeah. Yeah, so if I understand you correctly, then I agree. So if we go back to Monte-Carlo, so here's where the importance sampling came in, right? We said we gathered data with one policy, with pi prime, and then we use it to estimate the value of some other policy pi, and after we did the canceling, we ended up with this importance ratio, right? So what is this importance ratio, right? It's a product of all the policy probabilities that explain the return that we folded into our sample average, right? So this estimate of the value is based on a bunch of sample returns, right? And we're worried about the bias of these sample returns. So to correct for that bias, we compute this importance ratio, right? Take into account the policy probabilities that explain this whole return that we're using to estimate the value function. But in Q-learning, we're not using the whole return. We're bootstrapping off of the value of the next state, right? So the discrepancy between the policies plays no role, right? So here it doesn't matter what the policy is for the current state because this is a Q function. We specify we're interested in the value of some action A, right? And then immediately after that, we're going to bootstrap. So the policy probabilities for the future won't play a role. So this is nice because we can do off-policy learning without even having to compute importance ratios. Now, I should mention the caveat here, all of this holds only in this simple tabular setting that we're considering now. So these value functions we're learning, there are a bunch of values in a table with one entry for every state or state action pair. Tomorrow, when we talk about function approximation, things get more difficult, and if you want to learn off policy, you typically do need to do importance sampling, even with Q-learning. Okay, so this is what the Q-learning backup diagram looks like. So we started in this action, we got this sample next state, and then we take a maximization over the next action. So Sarsa's backup diagram would look like this one, except the black and open circles would be switched. So we would start with a black circle, the current action, and then we would look at the sample next state and the sample next action. And for expected Sarsa, it would be similar, except without this line here, because we would take a summation over the next action rather than a maximization. We have 8 minutes. What else do we need to cover? Let's see. I think we're going to make it. Okay, so this is a nice example from the Sutton and Bartow book that illustrates the difference between Sarsa and Q-learning. So here's the idea. It's called the cliff walking example. So you start in this start state and you want to get to the goal state. But there's a cliff here that you don't want to fall off. If you fall off the cliff, you get a big negative reward. Now, if you in this MDP, there exists an optimal deterministic policy which involves walking along the edge of the cliff. So the transition dynamics are deterministic, so there's no possibility of a misstep of like accidentally falling off the cliff. If you use an optimal deterministic policy, you can walk along the cliff to the goal perfect. However, during learning, you're going to need to behave stochastically in order to ensure sufficient exploration. So now the crucial question becomes, how do you interpret that exploration? If you use exploration during learning, and then later when you evaluate the performance of that policy, you keep the exploration on, the behavior will be different than if you turn the exploration off, okay? So what this plot shows is, on the x-axis we have learning, this is learning episodes, and on the y-axis we have the reward accrued by the policy we've learned so far when that policy is tested with exploration. So this is a setting that's specially designed to favor Sarsa over Q-learning. Because you might think, oh, Q-learning is just better than Sarsa because we don't have to do this, this epsilon soft nonsense. We can just learn off policy about the greedy policy even though we're exploring. But if we're gonna continue to explore, SARSA will perform better because it takes the exploration into account. So what will happen with Q-learning is we will learn the optimal policy is to go really near the cliff. But when we execute that policy, we'll add some exploration into account, exploration that was not taken into account by Q-learning because it learned off policy about a world where we weren't exploring. And then we'll be so near the cliff that exploration will take us off the cliff and accrue a bunch of negative reward. Whereas SARSA, we will explore during learning and we will learn the value under that exploration. So we'll figure out the best way to behave given that we are committed to exploration, which will be a safer path that stays far enough away from the cliff in order to ensure we don't fall on the cliff even when we're committed to this exploration. So which one you prefer depends a lot on how you're going to use the learn policy. Okay, so there's one more step to this puzzle, which is a whole topic unto itself, but I will just briefly mention. This is kind of like a middle ground between temporal difference methods and Monte-Carlo methods. So in TD0, which is the method we talked about, we have a backup diagram that looks like this. We were in some state, we took an action, we got a sample next state, we immediately bootstrap off that next state, okay? So what this does is give us a low variance but high bias estimate of the value function, right? It's low variance because we ignore all the stochasticity in the rest of the return by bootstrapping off of a value function that's, a fixed quantity. But it has a lot of bias because we're bootstrapping off a value function which is wrong. Right? The value function is something that we're itself learning, so especially at the beginning, we're basically bootstrapping off of garbage. So we have low variance, high bias. At the other extreme, we have Monte-Carlo methods, which are the other extreme. We have high variance, but no bias. So everything we're learning is completely data-driven. It's unbiased samples drawn from the actual world. So we have an unbiased estimator, but the variance is huge because we have so many sample returns, and each sample return involves so many stochastic steps. So we can optimize this bias variance trade-off by looking at intermediate points. So 2, 3-step, n-step returns where we wait some amount of time to bootstrap. That's some amount of time that's greater than 1 and less than infinity, less than waiting till the end of the episode. And there's a whole family of methods based on eligibility traces where we have basically different mixings of these n-step returns. So in eligibility traces, we have this parameter lambda, and lambda is like a weighting that determines how much we weight each of the different returns for different values of n. So this is the 1-step return, the 2-step return, and so on. And each of these will get a different weight, and that weight is determined by this parameter lambda. So TD0 is called TD0 because it's the algorithm you get when you set lambda to 0. That puts all of the weight on the 1-step return. And TD1, if we set lambda to 1, we get Monte-Carlo. We put all the weight on the true return. And lambda between 0 and 1 gives us some intermediate point that can balance this bias variance trade-off. And empirically, we see that lambda sort of around 0.9 tends to be the sweet spot. Okay, so that brings me to my last slide for today, which is a kind of unified view of everything we've talked about algorithmically. So here in this corner, we have dynamic programming. The backup diagram is wide but shallow because we're doing full backups based on our model, and we're bootstrapping immediately. Now, in the other corner, we have Monte-Carlo methods, the other extreme. We don't have a model, so everything is based on sample backups, and we're not doing any bootstrapping. So that leads to this narrow but deep backup diagram. Temporal difference methods give us the best of both worlds, where we don't need a model, so we do these sample backups. We still bootstrap using the Bellman equation. And this eligibility traces with this lambda parameter allows us to smoothly interpolate between 1-step temporal difference learning and Monte-Carlo methods in order to optimize the bias variance trade-off. And the final corner in this unified view is exhaustive search, which is a universally bad idea. So this is like the worst of both worlds. You have a model, so you can do full backups, but you totally ignore the Bellman equations. This is like the naive approach that dynamic programming improves upon. if I don't exploit the inside of the Bellman equation, I use my model to just like construct a bunch of returns without even noticing the relationship between the value of the different states that I'm computing from those returns. So don't ever do exhaustive search. All of these other methods have their place depending on what's available and what your assumptions are, what the details of the situation are. Okay, that's a whirlwind introduction to reinforcement learning. Tomorrow we'll talk about function approximation and building up to deep RL algorithms that are actually useful in practice. I look forward to seeing you tomorrow. Have a good day.